In this tutorial on industrial instrumentation, we will talk about pressure measurement part 5, and here we will talk about the various types of force balance pressure transmitters. The topics of discussion in this tutorial are force balance pressure transmitter, under which there are three types. They are dead weight piston gauge, ring balance gauge, and bell type pressure gauge. Pressure can easily be converted to force if we know the surface area on which it is exerted. The pressurized surface for a pneumatic system can be a bellow or a diaphragm. These devices normally have elastic elements as the pressure sensing surface. A balance force is generated for this type of pneumatic pressure meters in order to cancel out the applied force due to the applied pressure. The instruments which measure unknown by monitoring the balancing force come under the category of force balance pressure gauge. The force balance transmitters are more or less linear in nature and are capable to give continuous measurement. These devices have application in calibration of other pressure transmitters. Largely classifying, there are three types of force balance gauge, which are dead weight piston gauge, ring balance gauge, and bell type pressure gauge. The dead weight piston gauge measures pressure in fundamental units of force and area. Here, a piston which is made up of tungsten carbide is inserted in a closely fitting cylinder and weights are placed at one end of the piston. The device consists of an accurately machined and tightly fitted piston inserted in the bowl limb of the cylinder. The cross-sectional area of both the piston and the cylinder are accurately known. A platform is made where the balancing weight is placed to obtain the necessary balance. There is an oil reservoir at the bottom part provided with check valves. The oil is sucked up using displacement pumps on their upward stroke as and when required. The measurement range is between 20 kPa to 300 kPa with an accuracy of the order 0.1 millibar, that is 10 Pascal. New modified versions can measure pressure as high as 80 megapascal, but they are custom made and are not readily available. The pressure measurement takes into account the factors of errors due to the effective measurement cylinder area, buoyancy, gravity, and ambient temperature. The piston is fitted in the cylinder having a clearance of few millimeters and is rotated to minimize friction. The weight balances the applied pressure by the fluid in the piston fitted in the cylinder bow. The dead weight testers are so called as they use dead static fixed weights to determine the pressure in closed compressed fluid systems. In order to calibrate other transmitters, a known weight is first placed on the weight platform and then fluid pressure is applied using the plunger. The pressure applied is so adjusted that the weight is lifted. The tester calibrates the pressure by determining the weight or force and the area on which the force is applied. We first put the weight in the weight platform and then apply pressure using the plunger with the handle. The meter under calibration is affixed above the valve position as shown in the figure. The advantages of the dead weight piston gauge are that it is simple in design, construction and usage. It can be used to calibrate other pressure transmitters over a wide range. The fluid pressure is easily altered by adding weights or changing the piston cylinder combination. The limitations are that the dead weight tester accuracy is affected by friction between the piston and the cylinder. The measurement accuracy is dependent on the decimal significant value of the gravitational constant. The ring balance gauge was covered in the manometer pressure measurement segment. It is the second type of force balance pressure transmitter. It is used for measuring low differential pressure. The tube is made up of polythene or aluminum-based alloy or some other transparent material. It is bent in the form of a ring, supported at the center with a knife-edge pivot. The hollow tube channel is divided into two segments by spilling, sealing and filling with suitable light liquid, namely kerosene or paraffin oil. The two flexible tubings acting as pressure tabs P1 and P2 operate against the sealed walls and the ring rotates to balance the counterweight G. The calibration of the ring balance is obtained by means of balancing the weight G. It is the rotation of the ring that indicates the pressure difference. The differential pressure is indicated by the position of the partitioning wall A, and S is the flexible tubing distance indicating positive and negative differential pressure applied to the ring body, with small r being the radial distance. The differential pressure is determined by the following equation: del P equal to P1 minus P2 or Gs by Ar whole into sine alpha. The bell-type pressure gauge is the type of differential pressure meter. Here the force that is produced inside and outside the bell is balanced against a weight by spring compression. It is used for sensitive small range low pressure measurement. The range of pressure measurement for static pressure is 4 to 6 megapascal, and for differential pressure it is 0.06 to 4 kilopascal. The thickness, density and area of cross-section of the bell and the density of the sealing liquid, the elasticity of the spring arrangement are all calculated in order to find out the exact measurement range. The bell gauge finds application in low differential pressure measurement and in control of furnace and draft conditions. There are basically two types of bell gauge, and those are thick wall type and thin wall type. In the thick wall type, the sealed chamber is made up of cast iron filled with sealed liquid mercury. Here the inside pressure is higher than the outside pressure. In the thin wall bell gauge, the bell is thinner in construction and the control is achieved by means of a spring arrangement. Here, high pressure is applied at the outside and lower pressure is applied at the inside. The force difference due to the pressure causes changes in the length of the spring, eventually changing the position of the bell. The travel is proportional to the differential pressure. The range is determined here by the modulus of elasticity of the spring and the density of the sealing liquid. There are also other categories as single inverted bell element for static pressure, where the device is stationed at measurement point without atmospheric pressure compensation, and two element inverted bell gauge for differential pressure with atmospheric pressure compensation. In the single element bell gauge, only one bell jar is suspended in an inverted manner immersed in oil. As the pressure rises, the bell also moves up and balances a counterweight on the opposite end. This movement is transmitted via mechanical links expressed in pressure terms. The two-element open end of the bell-type gauge is covered by liquid as a seal, and it creates two chambers with applied pressures of P1 and P2. A higher pressure is exerted on the inside while a lower pressure is exerted on the outside of the bell jar. The bell jar rises till an equilibrium is maintained between the upward force and the balancing weight. As the bell jar rises, a smaller portion of it is immersed in the sealing liquid and the upward thrust due to buoyancy is reduced and apparently the weight increases. As the inside pressure is greater than the outside, it causes the outside level to be more than the inside liquid level, and the bell level rises. The bell level travel is proportional to the differential pressure. For more detailed and thorough reading, the readers can refer to the following links and references. Thank you.